Hi, welcome to another EC&M Tech Talk. Well, let's see. Today we're going to talk about how about reducing downtime? How about maybe minimizing the time we have to spend on maintenance work orders, work requests, trouble calls, service calls, whatever. How about making it a safer work environment? That's what we're talking about. We're going to talk today about the fundamental tests that we do when it comes to electrical maintenance. Now, those particular tests we're talking about, because who decides what those are, right? It comes from the NFPA 70B standard. The NFPA 70B is the standard for electrical equipment maintenance. 2023, it moved from a recommended practice to a standard. And we've talked about that before in our tech talks. Now, if I go through and I look at the NFPA 70B standard, it says on certain equipment, I must perform fundamental basic electrical testing. Okay, things like, in other words, if I have insulation on a piece of equipment, like an electric motor, let's do an insulation resistance test on it. If I have terminal connections, let's make sure those terminal connections are tight, secure, properly tightened, and that they aren't presenting any high resistance in my circuit, which is, of course, going to cause heat and potential, fire and safety issues, obviously. So how do they decide that? Well, NFPA 70B decides what electrical equipment, or helps you to decide, I should say, what electrical equipment you need to do maintenance on. And there are tables that can help you in NFPA 70B with that. Then once you decide what equipment you have to do maintenance on, the next question I would have would be, well, what maintenance do you want me to do, and how often do you want me to do it? And of course, the correct answer is, well, it depends, right? And so NFPA 70B helps you to set up that electrical maintenance program, which you're required to have anymore. It's required to be in writing, documented, in other words, and for electrical equipment that you deem needs to be maintained. Now, once you determine what that electrical equipment it is and how often to perform maintenance on it, the question is what maintenance to perform. That once again, there are certain basic electrical areas or testing that you have to take a look at and perform these tests. So that's what we're going to talk about. So the first topic we'll talk about then is that we're going to talk about bolted connections and terminations. As I said, if they're too loose or over-tightened or whatever, I can produce too much heat, cause overheating problems and so forth, and that's an issue for us. So we're going to learn how to test and inspect our bolted connections. Also covered in the NEC, alrighty, and 110.14D is in Delta. 110.14D talks about it. But we're going to talk about the maintenance issues today in 70B. Now, in addition to the bolted connections, the next topic we'll move into then insulation resistance. Okay, so we'll talk a little bit about insulation resistance testing. And then finally, we'll talk a little bit about infrared thermography, because 70B says, hey, that is a great predictive tool. Use it, all right? So we'll take a look at those requirements in 70B. So first of all, let's talk about bolted connections. So I've got a panel board back here behind me, right? And those panel boards, as you know, when on the circuit breakers, it gives me a torque requirement in inch pounds. So I could take, something like a torque screwdriver, right? And calibrated torque screwdriver is going to tell me, and I can tighten those terminals to a certain torque. Now, that's important not only on the terminal screws, but on the lugs, I think is really important where the power comes in on that panel board. So those large lugs at the top need to be tightened to a specific torque. If I under-tighten them, the problem is obvious. Too much resistance. Small increase in resistance, large increase in heat for the same amount of current flow. So I don't want loose terminal connections anywhere in my system. Also, if I over-tighten them, you might say, I can get them good and stuck. Man, I'll put a cheetah bar on this wrench, right? That'll get it, by golly. No, you don't want to do that either. Why? If I do that, when I tighten those threads that tight, I'm going to stretch them out. And if I stretch them out, it's not going to be a secure connection as if I had them tightened to their proper torque value. So I want to follow my whatever foot-pounds is of torque it is for those particular terminals. Now, in cases where you don't know what those torque values are, the NFPA 70B standard has 3 separate tables in it based on the the type of bolt that you have as to how tight you should make that up. You know, how many foot-pounds you should apply to it. Now, so we maintain the proper torque. We install it, we maintain the proper torque. How do we do that when we install it? 110.14d in the NEC says that I use a calibrated torque tool, or I can use things like breakaway bolts, where I have two heads on the bolt. I tighten it down. When that first head snaps off, then I know I have it tightened to the proper torque. But for maintenance, when I go back to verify the torque value on that, how do I do that? So 110.14 says, NFPA 70B says, when I go back to do maintenance on that, one way to check that torque connection, say on those bolts, would be to go ahead and get a torque wrench out and torque it down to what? 90% of that original torque value. Don't torque it back down to 100% when you're doing the maintenance. It tells us 90% of that original torque value. So that's one way that I can do it. Another good way would be infrared thermography, right? And we're going to talk a little bit more about infrared thermography in detail in the last section. But in infrared thermography, we're going to look at, for instance, in this single-phase panel board, it would be two separate lugs, one for each phase. And then, of course, we have our third as our neutral. And we can go in and look at the temperature difference between those three lugs. And if I have equal loading on my two phases, when I look at those two phases, I should have a maximum temperature difference of probably somewhere, depending on the loading and so forth, somewhere maybe 1 to 3 to 5 to 10 degrees C or something like that, depending on how similar the loading is. Now, if I have more than 15 degrees, so if I had 16 degrees C difference in temperature between those two phases where they come in, I got problems. That's too much temperature difference if those loadings are similar on those two phases. And then it says, you go ahead and shut the equipment down, man, and find out what's going on and fix it. You have a loose connection somewhere. And that's just going to get worse and worse and worse as time goes on, we know. Huh? So I can use my calibrated torque tools then. Another thing that I could do, I could have a temperature sensor mounted in there. I can buy temperature sensors, permanently install them on electrical equipment, and monitor connections and read it remotely. I can get an alarm if the temperature becomes too high on a certain terminal, or if I see a difference that's too great between two terminals. So anyway, there are options out there now to monitor temperature. I have my infrared thermography, and I have temperature sensors. I can torque the connections, I said. Or one other thing that I can do is, and I don't really do this on panel boards, but you'll see it more in switchgear. We can go ahead and shut it down and measure the resistance between the bolt head and, say, the bus bar. So if I measure the resistance between the bolt head and the bus bar, I get a value. If I use something, let's say, like the typical the typical mega-ohm meter, I'm going to get a certain value, right? And so I take one test lead and I'll put it on the bolt head. I'll put the other test lead on the bus bar. On an insulation resistance tester like this, the lowest value of resistance we might expect to read would be maybe 0.1 ohms. And that's as low as it can possibly read, 1/10 of an ohm. In reality, when I test those bolted connections, the resistance values are much, much lower. So if I were to take a multimeter and put on there, I would get 0, wouldn't I? But in reality, it's probably in the millionths of an ohm range. So I'm going to use a different meter for that. I'm going to use a micro-ohmmeter, what's sometimes called a digital low resistance ohm meter, or DLRO. On this micro-ohmmeter, it will read out down to millionths of an ohm. So that's what? 0.0000001 ohm would be 1 millionth of an ohm, or 1 micro-ohm. That's a pretty small value. So on my bolted connections, the typical values I might see would be somewhere in the range maybe 10 to 50 to 80 to maybe 100 micro-ohms. Now, often follow your manufacturer's specifications on your equipment. But so let's say if they specify something like 80 micro-ohms maximum reading or whatever, that's great. They may just say, well, take and add up or take a look at the three different resistance values, say on three-phase connections, A, B, and C, and then take and get an average from those and make sure you don't vary from the average by a certain amount. So it depends on whatever your manufacturer tells you. Follow those rules. There are the NETA test specifications, NETA maintenance specifications that give you a world of information, and some of you are probably well familiar with those. So anyway, follow your manufacturer's recommendations then when it comes to measuring the micro-ohm readings on your connections. And once again, we'll probably use those micro-ohm readings on things like switchgear bolted connections, bus bar bolted connections. Inside things like panel boards or disconnects and so forth, there we're typically going to use whatever the torque specification is the manufacturer requires us to apply. Alrighty? So that's bolted connections then, really. We have our infrared thermal sensors. We can measure the micro-ohm reading across the bolted connection if that's applicable. Or we can take a torque tool, calibrated torque wrench, whatever, screwdriver, and go in there and retorque that terminal at 90% of whatever that original installation torque value was, okay? Now, the next topic let's move into then is insulation resistance. It only makes sense then that if I have insulation will fail over time. All insulation will break down. I heat it, I cool it down depending on the type of insulation and so forth, and it begins to degrade over time. So I have to make sure that not too much current leaks through that insulation and out to the frame of my equipment. Let's take a three-phase motor, for example. Okay. So on a small three-phase motor, I've got insulation on the windings on the inside. I'm going to take into these terminals, they attach to the windings. So I can take something like my insulation resistance tester, find a good ground, connect one lead to ground, connect the other lead to either A phase, B phase, one at a time then. And then I can go ahead and apply voltage from my insulation resistance tester to those windings. And the current will flow into the winding. If any current leaks through the insulation and into my ground lead, my insulation resistance tester is calibrated to read out in ohms of resistance. Now, and many of you have performed these insulation resistance tests before. The two things that I see with insulation resistance testing. Number one is temperature corrections. The temperature of copper or metals will change the resistance values of that particular metal. So, as the temperature of the copper changes, the resistance value is going to change. So today, if I take my resistance reading at 18 degrees C, and next month I come along to do my maintenance, and I take my reading at 38 degrees C, how has that affected the resistance? Well, I don't really know. So I'm going to go ahead and correct my resistance values to a particular temperature. All right, so I'm going to use the tables that come with my insulation resistance tester and other resources and so forth that I can find, and make sure that I make my temperature corrections. The other big issue that I've run into with my insulation resistance testing is how long am I going to apply that insulation test voltage? When I apply my test voltage to my insulation and my windings, there are three currents that flow. There's dielectric absorption current, there's capacitive charging current, and then there's the actual current that leaks out into the windings. It's going to take a little bit of time for my dielectric absorption current and my capacitive charging current to stabilize out. So, once again, if I come along today and I take an insulation resistance reading and I let my tester run for 13 seconds and then I get a certain reading, next month somebody else comes along and does the same maintenance test and they let their tester run for 2.5 minutes while they go and do something else and then come back. Our readings may not be comparable then, right? The only real reading we're concerned about is the leakage current. So what we're going to do is we're going to do a spot reading test. We're going to go ahead and let our insulation resistance tester run for 1 minute and take a reading. That's our spot reading test. And if I do it that way today and you do it that way next month when you do the maintenance on this motor, or in 6 months, whatever, we'll be consistent. So correct for temperature and make sure that you do your readings properly. Now, time-wise. Also, on this particular insulation resistance tester, it has 2 buttons on it that I can push. One is DAR and one is PI. That's called the DAR is the dielectric absorption ratio. The PI is the polarization index. Polarization index, I let my insulation resistance tester run for 10 minutes, and I take a reading at 1 minute and 10 minutes. Dielectric absorption ratio test, I run for 1 minute, but the tester takes a reading at 30 seconds and again at 1 minute. It goes ahead and does the calculations for me internally into the meter and gives me a particular DAR or PI value on the face of the meter. I can use that for more advanced troubleshooting when it comes to insulation resistance testing. So, know your insulation resistance tester, know the equipment that you're going to test, right? Make sure that you're trained on that process and know how to do it. Obviously, safety is number one. We're going to de-energize any equipment before we do any insulation resistance testing on it. Finally, let's talk about the infrared thermography. Let's take a look at a couple of infrared thermography pictures. When we look at infrared thermography pictures, as I said, what we're looking at is on these images is the difference in temperature between 2 points. You may look at an infrared thermography image and go, whoa, that looks really hot. It's red. And the other one is dark blue, okay, or whatever it is, right? And that's not what's really important. In your software, you can take and hover over those images and so forth, hover over different points within those images and read the difference in temperature values. That's what you're concerned about. So generally 1 to 3 degrees C between 2 terminal points, we're not too concerned about, or not 3 to 15 degrees. Yeah, by the time we're getting up there towards 15, we're getting concerned with it. At 16 degrees C and greater between 2 test points that we're looking at on an image, it says go ahead and probably shut your equipment down, repair that as quickly as possible. Then you have something that's about ready to fail. But remember, there's a lot of things that go into that infrared thermography. You can buy infrared cameras that go on your smartphone. You can buy an infrared camera that's part of a multimeter. Or you can go out and you can buy some very sophisticated IR equipment, can't you? Now, depending on what you're doing in your facility, buy the equipment that meets your needs. Above all, make sure that you're properly trained on it. You can get certifications regarding electrical testing of your equipment and so forth, and doing interpreting your electrical images. Record all the data, keep track of it. Typically, we do infrared thermography every year, but depending on what your application is, of course, follow your electrical maintenance program as to what you need. The fundamental test is what we've been talking about. We've talked about the infrared thermography, we've talked about insulation resistance testing, and we talked about bolted connections. On the bolted connections, we can look at temperature, infrared, or temperature sensors. We can torque with a calibrated torque tool to 90% of that original value. We can measure the resistance through the bolted connection with our low resistance ohm meter. Now, if I have, and that's fine on our low voltage, less than 1,000 volts equipment. If you work on any medium voltage equipment, as many of you do, right? So for any medium voltage equipment, there's additional testing that you should perform as well. That's covered in the NFPA 70B standard, and it gives you a list of those tests the ones that you must perform. You must select from several different tests as to what you're going to perform. So on your medium voltage equipment, you may be doing things like high potential testing, high pot testing, VLF, very low frequency testing, tan delta testing, and so forth. Then we get into things like transformers, and we're measuring oil and testing oils, taking samples and sending them out for analysis and so forth. So anyway, there's a lot of testing that goes on in the electrical world, but the basic fundamental test is what's going to help to keep your facility safe, keep the equipment safe that you're working on, which in turn, by maintaining that equipment and doing these fundamental tests, you're going to reduce downtime, you're going to minimize unplanned outages, and if you do have to go out and do some maintenance troubleshooting, performing these basic fundamental tests will help you to identify problems, no doubt, a lot quicker than just Easter egging it, right? So, anyway, until the next Tech Talk, be safe.